Okay, so picking off where we left up in class, maybe just a little bit before we left off, we're looking at the force on a charged particle moving in a magnetic field. We learned the hand rule. The hand rule was point your thumb in the direction that the particle is moving in, point your fingers in the direction of the magnetic field, and the force will come into the palm of your hand. So in this case, the force would be acting down towards the bottom of the page. So if that's true then, so I have my particle moving in, and I'm just going to move it up here to move in. Moving in this way. But as it moves in, there is a force acting this way. Okay, so this is the velocity of the particle. And we talked about in class that if a force is pushing on something from the side, it's not going to speed the object up or slow it down. It's just going to make it change direction. And so instead of going, well, that might be a bit much. Instead of going, continuing to go straight, it's now going to go down at an angle. So if I use my hand rule again, thumb in the direction of the current flow, fingers into the page, there's still going to be a force here because it's still in the field. And the force is going to act this way. And the force acting this way is going to cause this guy to move like this again to make my field bigger. Okay, and so it's still in the field. And if it's still in the field, fingers this way, thumb to the bottom of the page, now the force, fingers off the camera, now the force will be going like this. Okay, which will cause this to curve again, this way. And again, if we do the hand rule, fingers in, thumb, the palm is facing the center, the force will be going like this. So as long as this charged particle stays in the field, the force will always stay perpendicular to the direction of motion, causing this particle to move in, you guessed it, to move in a circle. Okay? So the F would be here, and here, and here. So this force, then, is called the centripetal force. And the word centripetal means center-seeking, okay? Which means it's always pointing towards the center of the circle. And it's the force that keeps the object moving in the circle. If the object wasn't there, if the force wasn't there, the object would go at a tangent. So if this force wasn't pushing it in, this object would just keep going in a straight line path. Another example of a centripetal force is the gravitational pull of the sun on the planets. If that wasn't there, the planets would go at a tangent to the circle, straight line path out into space. Okay, so today we played with me swinging a stopper over our head, and we figured out what were the things that centripetal force was dependent on. One of the things that it's dependent on is the speed or the velocity of the object. How fast, speed, velocity is magnitude. How fast it's going. I guess magnitude, wrote magnet. How fast it's going. It's kind of dependent on its direction too, but that's always going to be, the force and the velocity vector are always going to be perpendicular. A second thing, since I spelled magnitude wrong, a second thing it's dependent on is the radius, the length of the string for the stopper, the radius of the circle. And a third thing that it's dependent on is the mass of the thing that's going in the circle. If I'm swinging a stopper or a person, it's going to be a very different force. And so from these three things, we get an equation, which we will get in Physics 12.1. Right now, I just needed to derive something else. But the bigger the mass, the bigger the force. The bigger the velocity, the bigger the force. The bigger the radius, the smaller the force needed. And actually, when we do this experimentally, we find out the velocity is squared. So this is the equation for centripetal force. It's dependent upon the mass of the object moving in the circle, the speed, and the radius. So what's causing this centripetal force for this particular object? Well, what's causing it is the force between a charged particle and an object, QVB sine theta. So what that means is that these two forces must be equal. So set QVB sine theta equal to mv squared over r. So in order for this particle to move in a circle, these two forces have to be equal. Sine theta is going to be 1 because theta is 90. All right, so we have QVB is equal to mv squared over r. All right, usually what we try to find here is the radius. So I have a v on this side, and I have a v squared. So one of those is going to cancel. I could bring my r up, and I could take my qb down, and we're left with mv over qb. This equation will allow me to find the radius of the circle that a charged particle will move in when it's entering a magnetic field. I just need the mass of the particle, its velocity, its charge, and its b. Really, I have almost all of them here in QVB sine theta. So when I tell you a charge is entering into a field, and I ask you about the path it takes, there are three things really I want. I want you to tell me it's going to be a curved path, that's one. I want you to tell me what the radius is, I actually want you to calculate it. And then I want you to tell me if it's going to be clockwise or counterclockwise. And that one's going to come from the hand rule. So in this case, this one's clockwise, right? And it comes from the fact you point your fingers into the magnetic field, your thumb to the side, the force is going to push it down. If it was a positive charge coming in, it would be counterclockwise because the force would push it up and it would curve the other way. So the three things when describing a path: 1, it's circular; 2, it's clockwise or counterclockwise; and 3, its radius is equal to whatever it might be equal to. Okay? Now that was what question number 24b was asking you. So if we go back to 24b, it said if the proton continues to move in a direction that is consistently perpendicular to the field, what is the radius of curvature of the path? And it tells you the mass of an electron is 1.67 times 10 to the negative 31. So if we go back to this question, number 24, then B, it's just asking you to find the radius. R is equal to mv over qb. So it tells us the mass is 1.67 to the negative 27. I might have said 31 there earlier, but proton, it's 27. The speed they told us was 3 times 10 to the 7th meters per second. The Q is 1.602 to the negative 19 coulombs, and the B was 0.1 of a Tesla. Okay, and so when you do the math, I think you get an R of 3.13. Sorry, just a 3.13 meters. Okay, so the equation then is R equals mv over qb. The one last thing, though, I should ask you to do is prove the units. Prove that the units of this side, oh, actually, I guess we should say where m is the mass of the charged particle. And of course, it's measured in kilograms. V is the velocity of the particle, of course, measured in meters per second. Q is the charge, measured in coulombs. And B is the magnetic field strength, measured in Teslas. And so then the question would be, can you prove the units? Can you prove that all of these will end up giving you the radius of the path, which should be measured in meters? Okay, so give it a shot. I have 30 seconds left, so I guess I'll make a new video with this on it, okay? So before you start the next video, see if you can prove these units, okay?